talk with you about axiomatic design, and our fifth edition of our text doesn't include this information. So I've put the URL that will point to the information that was in the fourth edition. I think this is an important thing for you to be aware of, and I'll tell you why in just a second. But I'll also put some more detailed information about axiomatic design on our SciPoint site so that you can read about it in a little more detail and see some more examples. Well, why do I think it's important to go over axiomatic design? Well, first of all, it's one of the few, if not the only, method in design that takes somewhat of a scientific approach to determining what a good design is. So people talk about design theory, but there really isn't a theory. This is about as close as we come to using a structured method in determining what a good design is. So I want you to be aware of it for that reason. Secondly, once you have a set of good designs, you can take a look at that set and determine which of those several designs is actually your best design, and that's not always easy to do. This method enables you to do that. And then finally, I think when you're aware of these kinds of approaches to designing, particularly one that's formalized and one that you can demonstrate in terms of its mathematical integrity, it gives you an advantage in your career. It also gives any company that you happen to be working for a competitive advantage by having engineers who know how to use this type of material. So there are a number of reasons that I think it's important, and so although the material's been removed from our text, I'd still like to spend just a few minutes with you talking about it. Well, let's start out talking about what an axiom is, and it's likely you've run into axioms in mathematics. And an axiom is an accepted, accurate observation, but it can't be proven. Another way to rephrase that would be to say that you can state an axiom, and if no exceptions or counterexamples to that axiom can be found, then it remains to be an observed truth. Theories, on the other hand, are a little more structured. You can answer the question, what would happen in the absence of this theory, with a theory, whereas with an axiom, it's not possible to do that. It's only an observed truth, whereas a theory can use its power in ways that are predictive. Well, what are these axioms in axiomatic design? Well, the first one is called the independence axiom. And what it says is that when you change a design parameter, ideally you would not be impacting the function that's associated with that design parameter. So a change in a design parameter would not result in a functional requirement of that design being changed. And we could state it formally like this. A design parameter can be adjusted to satisfy its corresponding functional requirement without affecting the other functional requirements. And in the second video, I'll show how we express that mathematically so that you can actually get a visual representation of how these changing design parameters can impact functional requirements. The second axiom in axiomatic design is a little more sophisticated. And it says that if you have multiple designs that meet the first axiom, you can choose the best of those designs by looking at the information content in those designs. And the best design among the ones that meet the first axiom will be those designs that have the least information embedded in them. Now, what's information and what's information content and how's it measured? Well, it's a fairly robust way of taking information embedded in a physical object and determining its binary value. And then you can also use probabilities to predict the likelihood that a particular design will fail to meet its functional requirement. But simply stated, in a very compact way, what the information theory says is that the design with the least information in it is the design that requires the fewest number of instructions. So a few instructions in terms of its assembly, few instructions in terms of its operation, all of those things would represent a design with a low information content. It's basically a measure of the design's complexity. Well, we take those two things, the fact that there aren't any coupled functions, I change one design parameter and I impact only a single functional requirement as opposed to multiple functional requirements. And if I have multiple sets of good designs, then I can take a look at the information content, and the design that has the least amount of instructions associated with it, or the least amount of complexity or information embedded, will give me the absolute best design. Well, how does this work? Well, it works in ways that are very familiar to you. We start out with what are called customer attributes, and we're accustomed to calling those things customer requirements or voice of the customer. So there are a number of terms that describe the same thing, but in the axiomatic literature, it's called customer attributes. And what those things are those features and requirements and needs of our customer. So they've come to us and said, I need particular design to do this, to solve this particular problem, and we as engineers take that set of customer attributes and now sit down and figure out ways to come up with functions that will respond to those customer attributes or wants and needs. Well, the functional requirements is that set of functions that we come up with, are typically verbs that will respond to the needs of the customer in terms of functional requirements. We call that the FR domain. Once we have the functional requirement domain defined, then we decide how we're going to combine machine components in either assemblies or sub-assemblies to meet those functional requirements. So now we're literally specifying or designing hardware in order to meet our functional requirements. And we can encapsulate what a design parameter is very simply by saying typically it's a noun. There's one more step, and that is the process variable domain. And we look at the process variable domain to help us decide how we're going to have to make or fabricate or manufacture this machine. And we can't really look at these individual domains as being isolated. We have to look across the domains to determine how one decision we make in a domain will impact domains both downstream and upstream from those domains. And I've shown you a picture here that shows the basic progression of mapping across domains. And we start, of course, with our customer attributes, develop a set of functional requirements, and then come up with a set of design parameters that will meet those functional requirements. And then, of course, we need to look at how those design parameters and their resulting components will actually be fabricated. And again, once we decide on a design parameter, we need to go back to see how that might impact functional requirements that aren't in the hierarchy of the entire functional requirement set. And that'll become clear what I mean by that in just a second when I show you a picture. So let's take a look at a customer who says to us, I want a device that was automated and I want it to remove metal from stock. And they want it to be powered. They want to allow for both rotation and translation of the stock. They want the operator of this machinery to be able to control the motion, the speed, and the positioning of the stock and of the machine itself. And they need all of the structures that will support the stock itself, the tools, and the machine itself. So we'd start out with this upper level, very general description of a functional requirement being remove metal. So we're going to start out with a very general, and we're going to go through this decomposition, through this hierarchy from general to specific, and we'll start out with this first layer of functional requirements and say, okay, well, our customer needed a power supply. They want it powered, so we'll have to think of a way to power this device. They said they wanted to control rotation and translation, so we're going to have to find a way to rotate this stock. We're also going to have to determine a way to control speed, to hold tools, to support both the tools and any structure required to hold the entire machine. And we want to think of ways to position the tool, the stock, and the tool and the stock relative to one another. So that's the first level of functional decomposition. And you'll notice now what we do is go into the next level of decomposition where we start to decompose those functional requirements in the first layer. So we're only doing one in this example, and we're looking at the tool support and holder. And we've decided, based on what we know to be true about this problem, that we need to look at ways to hold the tool itself, position the tool and stock, and support the tool and stock. So we're looking at functional decomposition of this upper level tool support and holder. And then we have a third layer of functional decomposition related to the holder itself. And we're looking at clamping, stopping the rotation, and holding the tool in this level of functional decomposition. So we went from general to specific and started decomposing functional requirements in each layer. Well, of course, you recognize this functional decomposition and the overall customer requirement of wanting to remove material as constituting a lathe. And so we would have the motor, which would provide transmission of power, the headstock, which would enable us to hold the stock and control the location of the stock in combination with the tailstock. We can control the speed with the gearbox. The bed provides support in part to the entire structure of the lathe in addition to the tools and the stock. And then the carriage helps us position and translate the tool and the stock. And then we broke down tailstock into its design parameters that made up these functional requirements for a tailstock. And we have a spindle assembly and a feed screw that helps us translate the stock. And then, of course, we have a frame which provides support to the tailstock. And then within the spindle assembly itself, we have other design parameters or other machine components that would constitute that subassembly. So we went from customer attributes to functional requirements to actually specifying design parameters that could be embedded in specific machine components. This is just a picture of a lathe, a schematic of a lathe that kind of points some of these design parameters out, the spindle and the headstock and the tailstock, the carriage and the lead screw. And then I also included the picture of the functional requirements so that you could draw the parallels between the design parameters, the customer attributes, and the functional requirements. Well, I'm going to stop there and let you think about these two axioms, the independence axiom, or the axiom that says ideally we should be able to change a design parameter and only impact a single functional requirement at a time. And then the second axiom would say once we have met the independence axiom, we can take a look at the information content or basically the level of complexity or the amount of instructions involved in fabrication and assembly and operation to determine the design that has the lowest information content. And from that we can pick out an optimal design. Well, we can represent these things mathematically, and that's what distinguishes axiomatic design in a lot of ways from other design methodologies. As I mentioned at the beginning of the video, this is as close as we have to an actual structured way of approaching design from a mathematical perspective. So in the next video, I'll show you how this is done mathematically and how you can use that mathematics to help you determine whether you've met axioms 1. In particular, axiom 2, the information axiom, we're not going to really demonstrate that mathematically because it involves a whole different set of probabilities and ways to measure information content using binary representation. So we're going to concentrate on axiom 1 in the next video.